Look at these two files for llama 3.18b. The F16 file takes 14.96 gigabytes. The Q4KM file takes 4.58 gigabytes. We save 10.38 gigabytes. That is why people quantize models. The file takes much less room. That name gives us a tempting guess. 4 bits is 1/4 of 16, so we might expect 14.96 gigabytes to fall to 3.74 gigabytes. The real Q4KM file is 4.58 gigabytes, which is 0.84 gigabytes larger. The size ratio is about 3.27 to 1. The file must store more than bare 4-bit weights. For this Q4KM recipe, the project reports a perplexity change of plus 0.1754. Perplexity is one way to score text prediction, and lower is better. The file got much smaller, while this one score moved a little. To explain both, we need to follow one weight into the 4-bit file. Here is the weight we pulled out, 0.19. In our worked example, it sits with minus 0.93, minus 0.52, minus 0.08, 0.63, and 0.96. These are teaching values, not llama data. For this 4-bit example, we replace each decimal with a whole number code from -7 to 7. Each code needs a real number meaning. The largest distance from 0 here is 0.96, so code 7 means 0.96. One step is 0.96 divided by 7, about 0.137. We call that step the scale. The 0 point is 0, so code 0 means real 0. Take 0.19, divide it by the scale, and add the 0 point. We get about 1.39. Our codes are whole numbers, so we round to code 1. That code only makes sense with the scale and 0 point. To read code 1 back, subtract the 0 point and multiply by the scale. The result is about 0.1371, the reconstructed weight. We began at 0.19, so the error is 0.1371 minus 0.19, about minus 0.0529. Code 1 cannot reveal which nearby value rounded to it. Run all 6 weights through the same steps. 5 move to nearby grid points, 0.96 stays exact. That movement is rounding loss. A weight beyond the grid gets clamped to an end, which is clipping loss. The grid's width affects the error. So next, we need to see how many weights share one scale. Keep the 6 weights under one shared scale. Now we add a made-up weight, 7.0, to the same group. The grid has to reach 7.0, so each step grows from about 0.13714 to 1. We still have 15 code positions, but they are spread across a much wider range. Watch 0.19. On the old grid, it became code 1 and reconstructed as 0.1371, with an error of about minus 0.0529. On the wider grid, it rounds to code 0, reconstructs as 0, and the error becomes minus 0.19. The wider range made the steps coarser for every smaller weight sharing it. Now separate 7.0 from the original 6. The 6 regain their 0.137 step, so 0.19 again reconstructs as 0.137 and its error returns to about minus 0.0529. The local fit improves, but now we must keep 2 scales instead of 1. Granularity is the choice of how many values share one scale. Q40 makes the cost concrete. It packs 32 4-bit codes into 16 bytes, then adds one 2-byte FP16 scale. That is 18 bytes for 32 weights, or 4.5 bits per weight. Smaller groups can fit local values more closely, but they need more stored scales. Grouping changes error size. Next, we need to ask which errors matter most to the layer output. Now, let's take 2 weight errors. In a small worked example, make both 0.05. An activation is the input number that a weight multiplies. Multiply one error by an activation of 1, and its contribution to the output error is 0.05. Multiply the other by an activation of 10, and the contribution is 0.5. Same weight error, 10 times the effect. Activation-aware weight quantization, or AWQ, looks for this pattern in sample inputs called calibration data. For each input number, it checks how large that activation tends to be. If one is often large, AWQ gives the matching column of weights more protection during quantization. The activations stay at higher precision. They only guide how the weights are quantized. Okay, but what does more protection actually mean? AWQ first uses a paired rescaling. Take a made-up weight of 0.24 and an activation of 10, their product is 2.4. Double the weight to 0.48 and halve the activation to 5. The product is still 2.4. Before any rounding, nothing about the layer output has changed. Now, put the before and after weights on a made-up grid spaced by 0.1. Without rescaling, 0.24 rounds to 0.2, so the product becomes 2.0, an output error of minus 0.4. After rescaling, 0.48 rounds to 0.5, with the activation at 5, the product becomes 2.5, an error of plus 0.1. Good, the protected channel's output error shrank. Still, more scaling is not always better. Push one channel too far, and its group may need a wider grid, making other weights round worse. In one author-run OPTIST 6.7 B-in3 test, a scale multiplier of 1 gave perplexity 23.54, 2 gave 11.92, and 4 gave 12.36. So AWQ searches for a balance. The bit width stayed fixed, where the error landed changed. Now return to the Q4KM file. Its name tells us how llama.cpp groups the codes and mixes tensor precisions. We are back at the file we started with, Q4KM, 4.58 gigabytes. The Q4 part says that most eligible weights use 4-bit codes. The whole file still averages more than 4 bits per weight, because those codes need the scale and range information we saw earlier. Next, K is llama.cpp's name for its grouped block layout. One Q4K block holds 256 weights, divided into 8 smaller groups of 32. Each group gets local range settings, so the grid can fit that part of the block more closely. Those settings also take space. Finally, M names a recipe that spends more bits on selected tensors. Most eligible tensors stay in Q4K, while selected tensor types use 5 or 6-bit encodings such as Q5K or Q6K. The exact mix can change with the model and llama.cpp implementation. Q4KM is therefore a mostly Q4K mixture. Now, the extra 0.84 gigabytes has an explanation. The llama.cpp table reports Q4KM at 4.8944 bits per weight on average. 4-bit codes make most of the saving. K, range information, and M's, higher precision tensors add storage. That is why the 14.96 gigabytes F16 file becomes 4.58 gigabytes, about 3.27 times smaller instead of 4. The size mystery is solved. The label still cannot tell us how closely the model will match F16 on a different job. The file size is settled. Now fill in the quality field. In an independent study, the AWQ method we already examined was tested on Ruler, a strict find the information task, across 5 llama and Qwen models. With 8,000 token inputs, those AWQ 4-bit models averaged 0.7 points below their matching BF16 versions. Close here. Now stretch the input to 128,000 tokens. With the same AWQ int4 setting, 5 models, and retrieval test, the average gap grew to 6.4 points below BF16. For these 5 models on this strict retrieval test, the 4-bit label stayed the same while the quality gap changed. So that label alone could not tell us the quality result. Q4KM explains why our file fell to 4.58 gigabytes. We still have to measure how well the model works on the task we care about.